only if the three conditions are all satisfied, you can say S is a subspace of Rn. Okay. We'll work on question A first. Now look at question A. Okay. R3, you treat R3 as a subset of R3, and then we're going to show R3 is a subspace of R3. So this one is actually easy. Okay. Again, we verify the three conditions. If I want you to show something, to prove something, you have to write proof or show. Okay. The standard wording in here is proof. We're going to prove R3 is indeed a subspace of R3. Okay. Again, the three conditions we need to verify. The first condition is you need to show S is closed under vector addition. The second condition is S is closed under scalar multiplication. The third condition you need to show is zero vector is in S. Okay. To say S is closed under the vector addition, we'll verify that first. Okay. You choose two arbitrary vectors from S, and then you want to show the sum of the two vectors is also in S. For this question, it's kind of obvious. Still, I want to write the full proof. Okay. We choose two arbitrary vectors from R3. Now I'm trying to verify the first condition. The first condition is we want to show S is closed under vector addition. Okay. We choose two arbitrary vectors from R3. We choose two arbitrary vectors from R3. Any vector in R3 is actually from the circled R3. We treat the circled R3 as a subset of the big R3. Okay. Actually, the two R3s are the same. I shouldn't have said bigger or smaller. You choose two vectors from R3. Any vector in R3 has three components, right? We choose two vectors from R3. One vector is in the form, let's say ABC. It has three components, ABC. Okay. You need to choose two vectors from R3. The two vectors may or may not be the same. The second vector, can I use DEF? Any vector in R3 has three components. We want to perform addition of the two vectors. We want to show the sum of the two vectors is also in R3. Okay. We compute the sum of the two vectors. Okay. The first vector has three components ABC, and the second vector has three components, let's say D and F. We add the two vectors. We perform a vector addition. So the first component is A plus D, and the second component is B plus E, and the third component is C plus F. As long as you have a vector with three components, then that's a vector in R3. So the sum of the two vectors in R3 is of course a vector in R3, right? This is kind of trivial. So later on we just call R3 as one of the two trivial subspaces of R3. I will make more comments later. Okay. Again, as long as you have a vector with three components, that's a vector in R3. Now look at the mouse cursor. So this is the standard notation in R3. Okay, that's a vector in R3. Secondly, the second condition we want to verify is R3 is closed under scalar multiplication. So this one is kind of obvious too. Okay. We choose an arbitrary number. So by that we mean, okay, sorry, I forgot to write something. After you see the sum of two arbitrary vectors in R3 is also a vector in R3. And then you can say S is closed under vector addition. Okay. After that, we say S is closed under vector addition. In the future, I just write a VA, okay, for vector addition. The second condition we want to verify is S is closed under scalar multiplication. Okay, so we do that. You need to show any number multiplied by any vector, the scalar multiple is a vector in R3. Okay. So this one is kind of obvious too, right? You choose an arbitrary number, can use K. So because I have used C earlier, so can use K for the arbitrary number. The same thing. I'm going to use K to denote an arbitrary number. For any number for any real number, actually for any scalar, it means for any scalar. Okay. And for any vector in R3, now let's say ABC. Any vector in R3 has three components, right? We want to calculate the scalar multiple of this number K and the vector ABC. Okay. We have, you use the number to multiply the vector. The answer is a scalar multiple. The answer to the scalar multiple is the first component is Ka, the second component is Kb, the third component is Kc. Okay. The resulting vector has three components. That's of course a vector in R3. So we have seen any number times any vector in R3 is again a vector in R3. And that's what we want, right? We want to show S is closed under scalar multiplication. Scalar multiplication. I'm going to use SM to denote scalar multiplication. Okay. That's the second condition. The third condition I want to verify is S. The zero vector is in R3. The zero vector is in R3. Okay. The zero vector in this particular case is the vector with three components, zeros, right? That's of course a vector in R3. As long as you have a vector with three components, that's a vector in R3. Right. We have verified all three conditions. And then, again, R3 is a subset of R3. We mentioned before, every vector in R3 is a vector in R3, of course, right? After verifying the three conditions, and then you can conclude R3 is indeed a subspace of R3. It's kind of noisy outside. They're shoveling snow. Okay, and then we say, therefore, R3 is indeed a subspace of R3. Any questions about this? Actually, there are two trivial subspaces of R3. In question B, I'm going to mention the other one, but the other one I'm not going to do the question in very detail, but I will show you the meaning. So that's not the question I want to talk about now. We'll move on to question B. Okay. In question B, you have another trivial subspace of R3. You see, for all the questions in question 2, we concentrate on subspaces of R3. Okay. As long as you can deal with R3, then you should be able to deal with R2. It's simpler, right? Now let's try to understand the set first. Okay. Again, for this question, I'm not going to show the work in very detail. This set has only one member, has only one element. I'm trying to use alternative terms for the member of the set. This set has only one member. Okay, and the one member is the zero vector in R3. We want to show the set consisting of only one member, the zero vector, is a subspace of R3. Okay, so that's what we want. Again, I'm not going to show the solution in very detail, but I will show the three conditions are all satisfied. Okay. Now condition 1, you have to choose two arbitrary vectors from S. You have no other choices. So because the set has only one vector, the zero vector, right? If you choose two arbitrary vectors, they may or may not be the same. They have to be the same. So in this case, right? So you just saw 0, 0, the zero vector, and then plus the zero vector is again the zero vector, right? It's kind of means S is closed under the vector addition. So by that we mean no matter how you add two vectors in S, the sum is also a vector in S. You see that, right? So condition 1 is satisfied. Again, I'm not going to write the full solution, but I'm showing you the meaning. Okay. And for condition 2, okay, so why not? I will give you the full solution. You choose two arbitrary vectors from S. You'll have no other choices. The two vectors, they have to be the same. So because set has only one vector, the zero vector, you choose two vectors from S, and then you add the two vectors. The sum of two zero vectors is also a zero vector, right? That's a vector in S. That shows S is closed under vector addition. The second case is not that trivial actually. For the second case, we want to show S is closed under scalar multiplication. So by that we mean no matter what scalar you choose, no matter what vector you choose from S, the scalar multiple is also in S. So that's the meaning of S is closed under scalar multiplication. Okay. So this time we choose an arbitrary vector. We choose an arbitrary scalar, arbitrary number. Scalar is the same thing as number. Okay. We choose an arbitrary scalar. We choose any number. We choose any real number. And then we choose any vector from S. You have no other choices. The vector has to be the zero vector, right? Now we want to compute the scalar multiple of the vector and the number. Okay. We have the scalar multiplied by the vector. Scalar multiplication, okay? You multiply all the components by the scalar of k. Of course, you have 0, 0, 0. That's of course a vector in S, because S has only the zero vector, right? After this, you'll say S is closed under scalar multiplication. And then lastly, we want to show the last condition is the zero vector is in S, right? Now look at the last condition. The zero vector in this Rn is a vector in S, the general case. Of course, the zero vector is in S, so in this particular case, because S is the subset of R3, consisting of only the zero vector, right? After we see all the three conditions, and then you can conclude. Therefore, S is a subspace of R3, right? Not every subset is a subspace, of course. So very shortly, I'm going to show you a few cases S is not a subspace. Okay. Now you look at the handout. I said there are two trivial subspaces of R3. One trivial one is itself. R3 is a subspace of R3 according to question 2a. We proved that, right? And in question 2b, I showed you the vector the subset consisting of only the zero vector is a subspace. Any Rn has two trivial subspaces. One is Rn, so itself. The other one is the subset consisting of only the zero vector. Actually, there's a name for that subspace. It's called zero subspace. This one is just called zero subspace. It's the set consisting of only the zero vector. Okay, it's a subspace. Actually, for question A, I forgot to answer the second part of the question. I will make it up. Okay, we'll add a new slide in here. The second part is I want you to get finitely many of vectors that span R3. That's a new term. Now concentrate. I'm going to tell you what the meaning. Okay, what we mean by finitely many vectors that span R3. Now we want to find two particular vectors. So in this particular case, we want to find. So how about that? I just tell you how many, and then you think about how to get me the vectors. In this particular case, R3 is a subspace of R3. If I'm looking for three vectors, finitely many three vectors, having the condition that I'm looking for three vectors in R3, in this R3, in the subspace of R3, okay, satisfying the condition that every vector in R3 is a linear combination of the three vectors. Anybody want to write the three vectors I'm looking for? Again, I'm looking for three vectors having the condition that every vector in R3 is a linear combination of the three vectors. Now I'm looking at the chat. So anybody want to tell me the three vectors you can give me? Tell me three vectors satisfying the condition that every vector in R3 is a linear combination of the three vectors. So please. You know that. Tell me a term. So tell me something, please. I'm looking for three vectors in R3, satisfying the condition that every vector in R3 is a linear combination of the three vectors. What are the three vectors I'm looking for? So please. Okay. I'm going to tell you. Okay. IJK. Okay. The three standard basis vectors. Okay. I will show you how. Okay. I will show you why, and then I'm going to tell you what we mean by the vectors span R3. Now the second part of the question, okay? We say something like we claim. Okay, that's right. We claim that the three standard basis vectors. Now let's recall the meaning of this. I know it's a little while before we learn this. The vector I has three components, 1, 0, 0, right? And the vector J has three components. Now let's say 0, 1, 0. And the vector K has three components. Now let's say 0, 0, 1. We mentioned before, so these three vectors are called standard basis vectors in R3, right? Now we want to claim these three vectors span R3. By that we mean every vector in R3 is a linear combination of ij and k. Okay. In fact, that's kind of the standard way to write math. So you want to claim some conclusion is true, and then to prove that you write in fact. Okay. And by the way, I told you at the beginning of the course, some proofs are required in this course. In fact, for each vector, so now let's say in R3, every vector in R3 has three components. So now let's say A, B, and C. For each vector A, B, C in R3, we just want to show every vector in R3 is a linear combination of ij and k. Is it true that every vector is a linear combination of ij and k? So now let's say A, B, C. Is it true that every vector is a linear combination of ij and k? To prove that, now let's recall the definition of the linear combination. We are looking for three numbers. I'm looking for three question marks, so that the equation is true. Anybody want to tell me the question marks now? Now I think you know what I mean. It's simpler now. How can we write any vector with three components A, B, C as a linear combination of ij and k? Yeah, probably you meant A, B, and C, right? I'm not trying to use X, Y, and Z. If you want to use X, Y, and Z, Y, and Z, you could change the notation here. A arbitrary vector, yeah, A, B, C. I think you got this. Okay, now I just want to convince you A, B, C, the vector can be any vector, actually, right? The following is not part of the proof. So, but 1, 2, 3 can be written as a linear combination of ij and k as 1 times I. Sorry, 1 times I. And then plus 2 times j, right? And then plus 3 times k. That's how we write 1, 2, 3 as a linear combination of the three vectors. But in order to say the three vectors they span R3, you have to show every vector is a linear combination of ij and k. You have no other choices to use some A, B, C or X, Y, Z. It doesn't matter. Okay. I meant the notation does not matter. So the three vectors ij and k, they span R3. Spanning R3, it means nothing but the every vector in R3 is a linear combination of the three vectors. So don't worry. So we're going to go over some more convincing questions. From that, you will see the meaning. Okay. Okay, now let's work on a typical question. Now let's say question C. Question C is actually a typical question. So not trivial ones. That's actually a non-trivial subspace. Okay, it's not R3 itself. It's not the zero vector. It's not the subset consisting of the zero vector. I mean, okay. We'll work on question C now. Now concentrate on Friday's quiz. You are going to see a question like that. So very similar. We want to show this one as a subspace first, okay, and then we find the finitely many vectors that span R, that span S. So this time S is the set, the subset of R3, consisting of all the three components. Now let's try to give a description. Okay, the first component can be any number. The second component can be any number. The third component is kind of dependent on the first two components. Okay, now let me try to show you what I mean. Okay, if the first component is 1, the second component is 2. Now listen to my question. Okay, in order the vector is in S, in order the vector is in the subset of S. Anybody want to tell me the third component? I'm going to make a vector in S. The second component is the third component is determined by the first two components. It's a plus 2b. Now a value is 1, b value is 2. A plus 2b, I think it's 5, right? It's 5. So that's a vector in S, right? Again, not all vectors are in S. So now let's say 1, 1, 1 is not a vector in S. It's not in S, I mean, okay. So because the third component is not the first component plus 2 times the second component. Okay. Yeah, that's why I said it's a non-trivial subspace actually. Okay, in any case, we'll show S as a subspace first. Still, so do not write solution, write proof if you want to write something. It's okay, I know many of you guys, so don't bother to write anything. Okay, now step 1, we're going to show S is closed under vector addition, right? We choose 2 arbitrary vectors from S. Now let's say one vector is AB, and the third component, in order the vector is a vector in S, the third component has to be a plus 2b, right? A arbitrary vector in S, and then we choose we need to choose 2 arbitrary vectors from S. They may or may not be the same, so you have to use different letters for the components. We use A and B, so can use CD. Another vector is the first component C, the second component D. The third, in order the vector is in S, the third component has to be C plus 2D. Is that right? We choose 2 arbitrary vectors from S. We want to compute the addition. We want to compute the sum of the 2 vectors. We perform a vector addition. The first component is A plus C, and the second component is B plus D, right? The third component, according to the definition of the vector addition, you add the corresponding components. The third component now is A plus 2B, and then plus C, and then plus 2D, right? Is that a vector in S? To convince yourself or to convince me it's indeed a vector in S, you have to show the third component is the first component plus twice the second component. Now let's do that. Okay. Now all we need is to rewrite the third component in slightly different form. I think all of you guys can understand this. The first component is a plus c. The second component is b plus d. We want to show the third component is 2 times the now let me try again. We want to show the third component is the first component plus 2 times the second component. By that we mean, now you look at the third component. Okay, the third component can be rewritten as a plus c. We regroup a and c. So we just change the order. Okay, number addition is commutative. It doesn't matter what order you want to use. It's a plus c, and then for these two terms, for the double underlined two terms, we can take out a 2, right? To write that as 2 times b plus d. Now look at the mouse cursor. Now do you see for the vector on the right hand side, the third component now is the first component. You look at the mouse cursor, okay? Plus 2 times the second component. That's how you say it's a vector in S. After you see that, again the vectors in the subset of S is characterized by the following property. The first component can be any number, the second component can be any number, the third component is the first component plus twice the second component. Okay, as long as you see that property, and then it's a vector in S, of course. Okay. We just verified S is closed under vector addition. Secondly, any questions so far? We'll do some more questions, so like that. Now let's try to finish the question first. Okay. The second condition is that we want to show S is closed under scalar multiplication, right? You have to choose an arbitrary number. Now let's use k for the arbitrary scalar. We choose an arbitrary scalar, arbitrary number, and we choose an arbitrary vector from S. An arbitrary vector from S has the form of the first two components can be any number. The third component is a plus 2b. Okay. Again, choose any scalar, choose any vector in S. We want to show the scalar multiple is in S. By that we mean any number times any vector in S. It's not out. It's still in S. I think you know the meaning. So what we mean by closed. The scalar multiple is closed, right? Okay, now let's check the condition. Okay, we want to compute the scalar multiple of any number and any vector in S. So we want to compute k times a b and a plus 2b. Right. Now the first component is ka. The second component is kb. Right. Now the third component is actually can I just write the third component? Okay, I'm not going to drop. I will try to write the thing in 2 steps. Okay, the third component, according to the definition of scalar multiple, the third component is k times a plus 2b. Right. You see, the third component can be rewritten as ka plus 2kb. Now look at the right hand side. Okay, it means the first component is Ka, the second component is Kb. Sorry, it's Kb. And then the third component is the first component Ka plus twice the second component Kb. That's how you can see that's a vector in S, right? So you see S is closed under scalar multiplication. We have verified the two conditions, the first two conditions, I mean. Any questions so far? The third condition, I told you last time, the third condition is kind of redundant. The third condition is redundant. It's actually implied by the second condition. You just take the scalar 0. But for some purposes, I want to include the third condition. I will tell you why I want to include the third condition soon. Okay. Now the third condition. We want to show the zero vector is indeed in S. Okay. That's the zero vector in R3. Now let's recall S is the set consisting of all the three-dimensional vectors. The first two components, they can be any number. I think the third component is a plus 2b, right? I'm just trying to help you recall the properties of the vectors in S. The zero vector is a vector in R3. We want to show the zero vector is in S. Is the zero vector in S? By that we mean is the third component the first component plus twice the second component? Of course that's true. Okay. To say that's a vector in S, you write the third component in the following form. That's the first component 0 and then plus 2 times the second component 0. You see 0 plus 2 times 0 is equal to 0, so the equation is valid. Okay. From there, we can say the zero vector is indeed in S. I was trying to write in S, not in. Okay. After verifying the three conditions, then you can say therefore S is a subspace of R3. Okay. Any questions so far? We have seen the three conditions are all satisfied, right? We still have the second part of the question. Okay, we want to find finitely many of vectors that span S. If you look at the question, we want to find finitely many vectors in S that span S, which means we are looking for. Can I tell you how many vectors we are looking for? By that we mean we are looking for, now let's say 2 vectors. If I'm looking for 2 vectors, having the condition that every vector in S is a linear combination of the 2 fixed vectors. You guys are smart. Anybody want to guess? Anybody want to guess what 2 vectors can span S? For the second part, we claim. So later on, I'm going to tell you how to get the 2 vectors. But now, if you can guess the 2 vectors, it's better. Anybody want to guess? We're looking for 2 vectors in S, satisfying the condition that every vector in S is a linear combination of the 2 vectors. Anybody want to guess? For this one, I'm going to introduce some notations. I will use U to denote the first vector. Should I introduce some notations? I'm not sure. So can I just use U to denote the first vector and use V to denote the second vector? Actually, for this one, it may not be necessary. Anybody want to guess, please? If you can guess, then you don't need me to tell you. If you cannot guess, I'm telling you now. Okay, I'm telling you now. Okay. Actually, the choices of the two vectors are not unique. There are many choices actually. The simpler choice, the simplest possible choice. I will tell you the simplest possible choice. Okay. Now look at the definition of the vectors in S. The first component can be any number. The second component can be any number. The third component is determined by the first two components. Okay. You make the first component 1. You make the second component 0. Anybody want to tell me the third component? If the first component is 1, the second component is 0. The third component, it has to be, in order the vector is a vector in S, the third component, it has to be the first component and then plus twice the second component. I know the question was too simple. Probably you guys don't bother to tell me the answer. But I'm trying to say, if the first component is 1, the second component is 0, then the third component is the first component plus 2 times the second component in order the vector to be in S. Okay. That's one of the two vectors I want to choose. At this point, anybody want to tell me the second vector? I told you, if you have two components that can take arbitrary numbers, if the third component is dependent on the first two components, by that we mean the first two components can be any number, can be freely changing. Anybody want to guess the second component? I mean the second vector? Second vector, please. The second vector, you just use a value of 0 and b value of 1. And in order the vector is to be in S, the third component has to be 2, is that right? The first component plus twice the second component is 2. Okay. We claim these two vectors in S, these two vectors span S. Span S. By that we mean we want to show every vector in S is a linear combination of these two vectors. In fact, can I write another weird word? Indeed. That's a wording my advisor, my PhD advisor, always use. Indeed. I'm going to use indeed this time. Okay, indeed. So this part is trying to prove that. Okay. We want to show every vector in S is a linear combination of the two vectors. So you have to choose an arbitrary vector from S. Okay. For every vector, let's say A, B, A plus 2B. For every vector in S, we want to write every vector in S as a linear combination of these two vectors. Now I'm looking for two numbers. Anybody want to tell me the two numbers? we chose two vectors. We want to show every vector in S is a linear combination of these two vectors. So please, I'm looking for two coefficients. I'm looking for two scalars. One may not be good. If you choose 1 the right hand side would be 1 3. Let's try again. Hardy. Try again, please. AB, right? Now you compute the right hand side, okay? Now you compute the right hand side. The right hand side, the first component is going to be A. The second component is going to be B. I think the third component is going to be A plus 2B, right? That's why the equation is valid. Okay, now for the second part, I'm going to summarize something, okay? I will summarize something. For the second part, we want to show S is, actually, for the second part, we are looking for finitely many of vectors, okay? Having the condition that every vector in S is a linear combination of the two chosen vectors. We want to choose two vectors, okay? That's what we meant by S is spanned by the two vectors. Okay. In general, to choose the two vectors, you look for which two components can be any number. In this particular case, A can be any number, right? B can be any number. So you set A value to be 1 and B value to be 0. I mean, AB value 1, 0 will determine one vector in S. The other vector we want to choose is set A value to be 1. Sorry, now let me try again. The other vector we want to choose is to set A value to be 0 and to set B value to be 1. Okay. In this particular case, set A value to be 0 and B value to be 1. In order the vector to be in S, the third component has to be 2. Okay. And then after you choose the two vectors, you have to show every vector in S is indeed a linear combination of the two vectors. Any questions? I will see if you know the meaning by doing one other question. Now let's do one other question, okay? Now let's work on question D. So question D is kind of simple. Now look at question D, okay? In question D, the first thing we do is to show this one is a subspace. I will do that a little quicker. I think we have seen a few questions already, okay? Now the proof. The first thing we do is to choose two arbitrary vectors from S for each vector. So now let's say A0, B. So that's a vector in S, right? We choose two arbitrary vectors from S. Now for this one, did I do something wrong? You have to choose two vectors. It's possible to choose 1, 1, 3, but for 1, 1, 3, if you want to show every vector is a linear combination of, let's say, the chosen vectors, it may not be too simple. we'll go back to that question. I'm going to make more comments. Okay. The way I told you how to choose vectors is the simplest way I told you earlier. Actually, it's possible to choose any. It's possible to use other vectors, but if you use other vectors, when showing every vector in S is a linear combination of other vectors, it may not be too simple. Okay. I hope I. Now let's work on this question first, and then we'll go back to that question. Okay. Okay. Now we choose two arbitrary vectors from S. One vector is A0B, and by the way, how can we characterize the vectors in S? As long as the second component is 0, then that's a vector in S. Okay. The second vector I want to choose is so maybe C0D. Okay. We choose two arbitrary vectors from S, and then we compute the sum of the two vectors. The first component is A plus C, right? The second component is 0. The third component is B plus D. To check if that's a vector in S or not, you just look at the second component. As long as the second component is equal to 0, then that's a vector in S. That's indeed the case, right? Now look at the mouse cursor. The second component is 0, so that's a vector in S. After that, you say S is closed under vector addition, right? The second condition, the same as before, we choose an arbitrary number, a scalar, an arbitrary scalar, I mean. And choose an arbitrary vector in S. So now let's say A0B. Okay, we want to compute the scalar multiple. Okay, so now let's say K times the vector A0B. For this one, I think the first component is Ka. In any case, the second component is 0. The third component is Kb, right? In order to say it's a vector in S, all we need is to do what? All we need is to check the second component. As long as the second component is 0, it's indeed the case. So that's a vector in S, right? And then you say, so S is closed under scalar multiplication, right? And lastly, the 0 vector is indeed in S. Again, you look at the second component. As long as the second component is equal to 0, then that's a vector in S. So we have verified the three conditions, all three conditions, right? Therefore what? Therefore, S is, we have verified all three conditions. S is a subspace of R3, right? So we're done the first part. Now, anybody want to tell me how to choose two vectors so that the two vectors span S? By that we mean every vector in S is a linear combination of the two chosen vectors. How can we choose two vectors? So just tell me the components, maybe, please. the first component, the first vector. So just tell me one of the two vectors, at least one of the two vectors, please. Anybody? So please, you know that. You just, yeah, 1, 0, 0 is right. Okay. So the other vector is 0, 0, 0, 1. It's kind of those. Okay. Actually, it's I and K. So that makes sense. Now to answer the second part, we claim. We say we claim. Again, you look at S. Okay. The first component can be any number. The third component can be any number. To choose one of the two vectors, you set A value to be 1, you set B value to be 0. To choose the other vector, you set A value to be 0, you set B value to be 1, right? I think 1, 1, 0, 0, that's actually I, right? And now let's say 0, 0, 1, that's actually K. We claim these two vectors span S. By that we mean every vector in S is a linear combination of these two vectors. Indeed, the part is to prove the claim. In fact, okay, but most people use in fact. Indeed, we choose an arbitrary vector from S, any vector in S. Now look at the definition of the vectors in S. The first component can be any number, the third component can be any number, the second component has to be 0. And just use A0B for any vector in S. We want to write every vector in S as a linear combination of the two vectors. Okay. So now let's say A0B. That's an arbitrary vector in S. Now we want to write the arbitrary vector in S as a linear combination of the two chosen vectors, 1, 0, 0 and 0, 0, 1. Now I'm looking for two numbers. So what are the two question marks? So please. What are the two question marks? The two question marks. So please, I'm looking. I want A and B, right? You see it's kind of always working. Now you can verify the equation is indeed valid. Okay. Probably for this question, I will tell you. I will make my point. It's possible to choose another pair of vectors. Okay. The span S. I'm trying to make my point that the choice of the two vectors is not unique. Okay. Instead of using and K, actually on Friday's quiz you're going to have a question like that. I give you two other vectors. I want you to show two other vectors can also span S. Okay. Now let's use one of the two vectors, 2, 0, 2, 0, 0. And we claim 2, 0, 0. Again, I'm trying to make my point. The choice of the two vectors is not unique. It's possible to choose two other vectors. Now let's say 0, 2, 0, 0, 2. These are the two vectors in S, right? These two vectors are in S. You just check the second component. As long as the second component is equal to 0, then that's a vector in S. We claim these two vectors span S. Now we are going to show that indeed or in fact. So this time I'm using indeed. Okay. Indeed, we want to show every vector in S. Every vector in S has the form of A. For every vector, now let's say A0C in S. Did I use A0B? I think I was using A0B. so it doesn't matter the notation. We want to write A0b, the vector in S, arbitrary vector A0b as a linear combination of these two vectors. You guys are smart. So tell me, so this time how to choose the scalars or the coefficients? Sorry. 2, 0, 0. And then plus another number times 0, 0, 2. I'm looking for the 2 question marks. So this time, tell me the 2 question marks. The 2 question marks, please. What are these two numbers? What are the 2 question marks this time I'm looking for? So please. I'm looking for 2 question marks satisfying the equation. This time AB may not be too good. So you compute the right hand side if we choose AB. A times 2, 0, 0, and then plus B times 0, 0, 2. You would get 2A. The second component is 0, so no problem. The third component could be 2B, right? This is not the same as the left hand side. Now I'm looking for 2 numbers satisfying the equation. Half of A, half of B is good. Okay, I will make more comments. Half of A is good. Half of B is good. So this time you compute the right hand side. You would get half of A then times 2. So you have A0, 0, right? And then half of B times 0, 0, 2. You would have 0, 0, B, and then you are going to have the left hand side, right? So which is the left hand side? Yeah, that's how you choose the 2 numbers. But you do not have to show this as long as you give me the 2 coefficients showing every vector in S is a linear combination of the 2 chosen vectors. First of all, you choose 2 vectors, and then you show every vector in S is a linear combination of the 2 chosen vectors. And then it means every vector in S is a linear combination of the 2 chosen vectors. It means the 2 chosen vectors span S. So the 2 vectors and they indeed span S. Okay. Actually, we have seen a few subspaces, but now I want to show you a few subsets that are not subspaces. Okay. Maybe we'll move on to question F. I will show you at least 2 particular cases the set is not a subspace. Okay. Now you look at this S. Okay. The subset. Now how can we describe the subset? The first component can be any number. The second component has to be 0. The third component is 1 more than the first component. Okay, now let me try to get a vector in S. If I give you the first component 2, the second component 0, the third component, it has to be 3 in order the vector to be in S. Again, to characterize the vectors in S, you just check. Actually, you check 2 things: the second component it has to be 0. The third component has to be one more than the first component, right? We want to show this one is not a subspace. Actually, in past years, I used to ask people to guess it's a subspace or not. But now I'm going to simplify that thing. I will tell you it's not a subspace. You tell me why. Okay, now let's look at the definition here. To say S is a subspace of Rn, in that particular case R3, you have to say all three conditions are satisfied. I hope it makes sense. To say S is not a subspace, you just need to say one of the three conditions is not satisfied. So that makes sense? In order to prove S is a subspace, you have to say all three conditions are satisfied. To say S is not a subspace, you just say not all three conditions are satisfied, which means you just say one of the three conditions is not satisfied. Anybody want to tell me, in this particular case, which one of the three conditions is not satisfied? Which one of the three conditions is not satisfied? The third one. Yeah, that's good. The third one. The zero vector can never be in S. So because the third component is one more than the first component, the zero vector is never in S. Right? Yeah, that's the partial reason why I want to include the third condition in the definition. Okay, now you just say proof. S is not a subspace because the zero vector in this particular case, the zero vector in R3 is not in S. Again, the zero vector is not in S. So because the third component is not one more than the first component, right? That's it. Which means one of the three conditions is not satisfied. It cannot be a subspace. Okay. Easy? We'll look at one other subset that is not a subspace. That's question G. I'll look at G. Okay. Okay, now you take a look at the definition of the subset. I mean the members of the subset. This means the product of the first two components is equal to 0. By that we mean to check if a vector is a vector in S, you multiply the first two components. If the product of the first two components is equal to 0, then that's a vector in S. Now let me try to ask you a few questions. Is 1, 1, 1 a vector in S? Is 1, 1, 1 a vector in S? You multiply the first two components, 1 times 1. It's not in S, right? 1 times 1 is equal to 1, so which is not 0. So it's not in S. Now let me ask you one more question, okay? So maybe two more questions. Is 201 in S? Is 201 in S? Is 201 in S? You multiply the first two components. This time you have 2 times 0, so which is 0. The product of the first two components, product of the first two components is equal to 0. So that's a vector in S. Right. One more question. So please try to answer my question, okay? Is That's not what I meant. It's 0, 0, 3, 0 in S. It's 0, 3, 0 in S. It's 0, 3, 0 in S. You multiply the first two components, right? That's indeed a vector in S. So because 0 times 3 is equal to 0. Okay, now let me try to tell you under what condition the vector is in S. So because you want the product of the first two components it to be 0 in order a vector it to be in S. So what you do is to under what condition the product is equal to 0? Can I just say the condition at least one of A and B has to be 0, right? I mean at least one of A and B, at least one of the first two components is equal to 0. That is a condition under which the vector is in S. I hope I made the thing clear. Again, in this case, I want you to show S is not a subspace. By that we mean I want you to tell me one of the three conditions is not satisfied. Okay. Actually, I can tell you in this case, condition 1 is not satisfied. By that we mean we want to show S is not closed under vector addition. To show S is not closed under the vector addition, you do not choose two arbitrary vectors. You choose two particular vectors in S, and then you want to show the sum of the two particular vectors is not in S. I'm going to repeat. We are going to choose two particular vectors in S, satisfying the condition that the sum of the two particular vectors is not in S. I think you guys are smart. So anybody want to tell me how to choose two particular vectors from S such that the sum is not in S? How about we choose 1, 0, 0, 1, 0, so whatever number 1, okay? That's a vector in S. We can choose one other vector. So now let's say 0, 2, 2, 3. That's also a vector in S, right? As long as one of the first two components is equal to 0, that's a vector in S. I just told you that. These are the two vectors in S. I do not have to write 4, okay? These are two vectors in S. And then you can say, but you add the two vectors. Now let's say 1, 0, 1 and 0, 2, 3. You see the sum of the two vectors is 1, 2, 4, I believe, right? You add the corresponding components. Is the sum a vector in S? The product of the first two components is not equal to 0. That's not a vector in S. Okay. I know this part could be a little confusing for some of you guys. I'm going to write a summary how to prove a subset is not a subspace. Okay, so to show, so now let's say a subset I will go back to the question we just did earlier. Okay, to show a subset of Rn in general is not a subspace. We need to show that at least one of the three conditions in the definition is not satisfied. Okay. You just have to show one of the three conditions is not satisfied. Okay. And then, so there are three particular cases. The first particular case is how to show S is not closed under the vector addition. To show S is not closed under vector addition, all you need is to choose two particular vectors in S such that the sum of the two vectors is not in S, like we just did. These are the two vectors in S. These are two particular vectors in S, but the sum is not in S. That means S is not closed under vector addition, right? And the other case, the second case, you just have to show one of the three conditions is not satisfied. But in some cases, you have to show S is not closed under scalar multiplication. Okay. To show S is not closed under scalar multiplication. So what you do not have to show every number and every vector. So this time you choose a particular number scalar, a particular scalar, and a particular vector in S. Such that the scalar multiple is not in S.